Good morning students, welcome to another lecture on microprocessors and microcontrollers. Today we are going to discuss about the features of MSP430 family and a block diagram of MSP430 family. And in this lecture I am going to deliver only a few blocks which are present in this block diagram, and the remaining session will be in the next part. As we have already seen that based on the different RAM and ROM categories, we have divided the MSP430 families. Today we are going to discuss about MSP430 families and its features. Here we are going to discuss about MSP430X5X6 microcontrollers, and based on the flash memory and power consumption and device parameters, here are the specifications of that family, that is MSP430 which is in our syllabus. So here flash based ultra low power microcontroller units, that means based on the RISC architecture, it is a 16-bit RISC architecture which operates with a clock frequency of 25 MHz and also works with the low voltage from 1.8 volts to 3.6 volts, and it is also having a flexible power management system. Flexible means which can be reliable, so which can be affordable. The main theme is in order to operate in low power, high speed. Okay, coming to the power specification, it is as we have already known that 0.1 microamps for RAM retention, 2.5 microamps for real-time clock mode, 165 microamps per million instructions per second when it is in active mode, and less than 5 microseconds for wake up time, which is very handy, or which is very useful. And also the device parameters, like it has a flash RAM which is extended up to 512 KB, and RAM options up to 66 KB, and an A to D converter options 10-bit and 12-bit, and also the general purpose IO pins, that means ranges from 29 or 31 or 47 or 48 or 63 or 67 or 74 or 87, that means based on the usage these pins may be varying. So coming to the architecture or a block diagram of MSP430 family, here in the previous session we have discussed about the MSP430. In the same sense, here we have a different family with the different blocks, and the timers will be varied. Here coming to the first one, unified clock system. By seeing this diagram, we can find that there are 3 clock cycles. These 3 clock cycles are used, or these 3 clock cycles will provide a clock frequency in order to run these devices. Here UCS is providing 3 various clock cycles, which are SMCLK, ACLK and EMCLK. Using these clock signals, the user can select the best balance of performance and lowest power consumptions. Which one is useful if I am using MCLK, and at the time I am not using these 2 clock pulses. If I am using ACLK, at the time I am not using MCLK. So if we are using all the 3 clock cycles, it is going to consume more power. So in order to reduce the powers, once it is using MCLK, then it will not be in use. So coming to the next one, this is a CPU, XVU and working registers. This is a CPU here. And coming to the next one, embedded emulated module. Here EM is nothing but embedded emulated module, and this is accessed and controlled by a, see here, JTAG or SBW. JTAG instance, Joint Test Action Group. It is a device which is present in a small ICs, which in turn tests itself before going to the execution or SBW instance spy bywire mode. Sorry, spy bywire mode. That means these two will interface with the EEM in order to execute a program or access through the controller. And coming to the flash memory and RAM, here it is varying. That means either it may be 32 KB or it may be 64 KB or it may be 96 KB or it may be 128 KB, depending upon the flash. We can vary the flash ROM, not RAM, ROM. So we can vary these things. In the same sense, we can vary the RAM values as 4 KB plus an external of 2 KB, 6 KB an external of 2 KB, 8 KB and an external of 2 KB. So these can be varied according to its requirements. Next one is power management module, and this manages all the function related to power supply and its supervision for the devices. So here SVS supervision, that is, here it is going to check, it is going to supervise how much power is going to be used. In the power management module can also integrate a low dropout regulator. That is, here is a LDO is nothing but a low dropout regulator, that means which consumes less power. And the SVS, that means this is used to monitor the supply voltage or an external voltage, or the external voltage drops below user selected threshold. This will checks all the power which is used by the microcontroller, whether it is high or it is low. It will control everything. It counts everything. And coming to the next one, and it also counts the here we have a brownout reset, that it detects low power supply voltages. Here this brownout detects low power supply voltages such as when a supply voltage is applied or removed from PC's terminal. If it is there is a supply voltage, if we remove the supply voltage, then what will happen? It is going to detect that one, and the brownout reset circuit resets the devices by triggering POR, power on reset signal, so that the power is applied or removed. Suppose the power is applied, so it will get reset. If a power is removed, we are going to check again. We have to start from the basic. So coming to the Watchdog Timer and IO ports, this is a very important thing. And our next upcoming 4th chapter is all based on IO ports of MSP430. So please concentrate on these things, and I'm going to discuss about these two in detail in the next class also, or in the upcoming chapters also. Here I am giving just a brief out of a Watchdog Timer and the IO ports. Here a Watchdog Timer is an electronic timer which is used to detect or to recover from computer malfunctions. Here malfunction is nothing but the device which performs or which is used to recover, which is used to get back to the main function. And also this Watchdog Timer module restarts the system on occurrence of a software problem, or if a select time interval expires. It will restart, means suppose if there is any error, sometimes the system manager itself asks, there is a problem in your software, can I restart now? Or sometimes if you are going to insert, or if you are going to install, if you have installed any new software, it is going to ask that in order to work on the new installed application or new installed software, the system has to be restarted. That will be done by this Watchdog Timer. And also During normal operation, the system regularly restarts the watchdog timer to prevent the elapsing or timing out conditions here. So if a system fails to restart the watchdog timer due to any one of the hardware faults, the timer will elapse and generate a timeout signal, so that the timeout signal is used to initiate the corrective actions like placing into a safe mode or restoring into its normal system operation, so that it will be refreshed or it has to be restarted again. And also the watchdog timer also is used to generate a timely interrupts for an application. Suppose if you need any timely applications, instance if you need any refreshing, it is going to generate it automatically. So coming to the IO ports, here we have port A, port B, port C and port D. So here we have port 1, port 2, port 3 and port 4. And in the same sense we have 8 ports, that means here port 1 or port 2, port 3, port 4, port 5, port 6, port 7, port 8. In the family of MSP430 this has 8 ports from P1 to P8, and P1 to P7 has 8 IO pins, and P8 has, this one has only 3 IO pins, and each IO pin is individually configured for an input-output operations. What is in IO input or output? So we can, by using these ports we can access the data, or by using these ports we can send the data. So each IO pin is individually configured for input or output direction, and each IO line can be individually read or written into. All the individual ports are configurable with a pull up and pull down resistors, as well as configurable for drive strength. Here coming to the pull up and pull down resistor, the topic will be explained in the next chapter, and how it is going to be used and how this watchdog timer is used. Okay, and coming to the port 1 and port 2 have interrupt capability. So here port 1 and port 2 is also having interrupt capability, and each interrupt IO lines can be individually enabled or configured to provide an interrupt on a rising edge or falling edge of a signal. So here we are enabling an interrupt or configuring. What is the meaning of configuring? Preparing a device to work with other programs also, or in order to respond. Suppose if you are using 8086, the program which was returned in 8085 can also be worked. That means we are going to configure the device in such a manner that previous versions also will work on the same newer version. Okay, that in the same wise we are going to enabling the each and individual pins in the ports for doing the work at the rising and falling edge of a input signal, and each individual ports can be accessed as a bitwise or can be combined into a word wide. That means if the data is 8-bit, it is in 8 bits, or a word wise we are going to access complete 8 bits, and also accessed via formats. That means port pairs are P1, P2, and where we are using port pairs, we are combining these two things. See here port 1 and port 2 are combined here. You can write it as a P1, P2 port, P3, P4 port, and we are combining it as a PA. That means P1 and P2 are called port A, P3 and P4 called port B, P5, P6 called port C, and P7, P8 are called port D respectively. So coming to the next one, full speed USB. Here USB means universal serial bus. This full speed universal serial bus transceivers physical layer interface. Physical layer interface, that means we are what is an USB? That means we are connecting to a physical and our external interface that suppose control interrupts and bulk transfers. This is also all used for controlling the interrupts and also to transfer bulk data, and this supports suspend and resume or remote wake up intervals. We can disable this one, or we can enable this one, or we can wake up it instantly by enabling that one. And it is integrated with a voltage of 1.8 volts to 3.3 volts, which is a very low dropout linear regulator, and it is integrated programmable logic levels which are worked with a very highly flexible clock frequencies, and also can be used a 2 kb of dedicated USB buffer. If this USB is disabled, that means if this USB port is disabled, then a 2 kb buffer space is mapped into the RAM, and USB pins can be also used as an general purpose IO pins. If this is enabled, then a 2 kb is buffered space from 2 kb is a buffer space from mapped into the RAM, and these USB pins are used as an general purpose IO pins. So coming to the next one, that is a MPY32. That is, what is the MPY? Multiplier 32 bit. Here this MPY32 bit is a peripheral and is not a part of CPU. It is not a part of a CPU. This means it is it activates or its activities does not interface with the CPU architecture. Here it is not at all interfacing with the CPU architecture, and it performs a signed and unsigned multiplication of a 8-bit or 16-bit or 32-bit or 24-bit operations. And coming to the timers, we are going to discuss it in the next session.